welcome to this explainer. Okay, imagine for a second that you're a forensics expert walking into a totally cold case. You can't actually see the culprit, right? But you do have the fingerprints they left behind at the scene. Well, in the microscopic world of chemistry, we do exactly the same thing. Today, we're decoding molecular crime scenes by diving into the truly fascinating world of hydrocarbon fragmentation. This is literally the exact same science used in anti-doping labs, pharmaceutical drug discovery, and real-world forensic investigations. It's such a compelling puzzle, isn't it? How do you uncover the exact structure of a molecule when it's just way too small to see? Well, the answer is you throw it into a high-energy interrogation room. That's essentially what a mass spectrometer is. We blast a molecule to pieces and then examine the shattered remains to figure out exactly what it looked like before the blast. Every single jagged line you see on a mass spectrum graph, that is a vital clue.
Okay, let's dive into this. Here is our detective's notebook for today. 1. The initial ionization event. 2. Alkanes, chains and branches. 3. Cycloalkanes, breaking the ring. 4. Alkanes and alkynes. And finally, 5. Aromatics and tropylium ions.
Let's kick things off with Section 1, the initial ionization event, bombarding the molecule. So to get our clues, chemists use a pretty violent technique called electron ionization mass spectroscopy, or EIMS. Basically, a sample molecule gets absolutely bombarded by high-energy electrons inside a vacuum chamber. During this massive, intense collision, the molecule is forced to give up one of its own electrons, which turns it into a highly excited radical cation. It absorbs a huge amount of extra energy, and under all that incredible strain, it literally shatters into smaller, detectable pieces. We call these broken pieces fragment ion. But here's the catch. Which of those pieces actually survive long enough to be detected by the machine? That brings us to Stephenson's rule, which is basically the golden rule of molecular survival in the mass spec. This rule dictates that the fragments forming the most stable carbocations are the ones that actually survive to make it onto our spectrum. Just as a quick refresher, carbocation stability completely depends on how many other carbons are attached to the positively charged carbon, right? A tertiary carbon, one attached to 3 others, is way more stable than a secondary or primary one. So fragmentation processes that lead to highly stable ions are heavily favored, while the really unstable pieces just vanish or break down even further.
Moving right along to Section 2. Alkanes, chains and branches.
Take a look at this mass spectrum for straight-chain octane. Do you notice those clusters of peaks moving from right to left? If you look closely, they're separated by exactly 14 atomic mass units. That 14 AMU difference corresponds exactly to the loss of a CH2 group. Because octane is a long, straight carbon chain, it breaks into highly predictable chunks. It's honestly a lot like snapping a long Lego bridge into uniform, regular pieces. You can also clearly spot the molecular ion peak on the far right at MZ114, which tells us that a pretty good portion of the original unbroken molecule survived that initial blast. And this brilliantly illustrates what happens when we introduce branching into the molecule. Over on the left, we still have our straight-chain octane, but on the right, we've got isooctane, a highly branched isomer with the exact same molecular weight. Now look at the far right of the isooctane spectrum. Notice anything? The molecular ion peak at 114 is completely missing. Why? Because branched chains snap so much more easily to form those highly stable tertiary carbocations we talked about. That massive spike you see at MZ57, that is the extremely stable tert-butyl carbocation. The branched molecule breaks apart so favorably and so fast that the intact molecular ion practically doesn't even exist long enough to be detected. All right, let's open the next file. Section 3, cycloalkanes, breaking the ring. Here we have the spectrum for cyclopentane. Now, rings are naturally pretty tough to crack because you have to break not 1, but 2 carbon-carbon bonds to actually shatter them. Because of that, a much larger proportion of cycloalkanes survive the interrogation completely intact. That gives us that really strong molecular ion peak you see at MZ70 on the right. But when the ring does finally break under pressure, it has a very specific signature move. It predictably loses a neutral molecule of ethene. That M-28 loss accounts for the massive, towering base peak you see sitting right at MZ42. Now, if you add a side chain to that ring, you create an obvious vulnerability. Take a look at methyl cyclopentane. While it does still lose ethene, which you can see again at MZ56, the absolute most favorable mode of fragmentation is losing that methyl side chain entirely. The crucial clue here is that massive peak at MZ69. When a ring has a tail, chopping off that tail is simply the easiest way for the molecule to stabilize its positive charge in the gas phase.
Let's see how double and triple bonds change the game in Section 4, Alkenes and Alkynes, the pi bond influence. When we interrogate alkenes and alkynes, the spectral data follows a very specific set of rules. We usually see distinct molecular ion peaks because the pi bond actually absorbs that initial electron loss, leaving the main carbon skeleton relatively undisturbed. The location of these double and triple bonds completely dictates where the molecule is going to shatter. They act almost like molecular directors, forcing the cleavage to happen where it will form resin-stabilized ions, like allylic and propergillic cations. Oh, and for terminal alkynes, we see very distinct super strong M-1 peaks.
Let's actually look at this in action. Check out this spectrum for 1-pentyne, which is a terminal alkyne with a molecular weight of 68. Direct your eyes straight to that massive base peak on the far right at M/Z67. That is our strong M-1 peak, and it's caused by the extreme ease of losing just a single terminal hydrogen atom to form a stable ion. You can also spot the propargyl ion totally dominating over at M/Z39. So the triple bond is acting as both a shock absorber and a structural director, completely controlling the fragmentation pattern. And finally, our last case. Section 5, aromatics and tryptolium ions, the ultimate disguise. Now what's really interesting about this slide is the spectrum for toluene. Toluene has an intact molecular weight of 106, which you can clearly see as a nice strong peak on the right. But look closely at that towering, intense base peak at MZ91. You might logically think, oh, this is just a simple broken piece of toluene, probably a benzyl carbocation where the methyl group lost a single hydrogen atom. And honestly, that makes sense. But intricate isotope labeling experiments proved that something much stranger and way more elegant is actually happening here. It turns out the molecule literally rearranges its entire identity midair. Instead of staying as a 6-membered benzene ring with a positive carbon tail, the ring spontaneously expands. It forms what we call a tropylium ion, a highly stable, 7-membered delocalized aromatic ring. It essentially dons this ultimate disguise to survive the mass spectrometer's violent interrogation. This extreme stability is exactly why that MZ91 peak completely dominates the spectrum of alkyl-substituted benzenes. It's just an absolutely brilliant survival strategy in the gas phase. So we've cracked the case on alkanes, we've broken open cyclical rings, we've tracked down the directing power of pi bonds, and we've unmasked the shape-shifting tropylium ion. It really makes you wonder, right? What other molecular secrets are just waiting to be decoded in the explosive fragmentation patterns all around us? From the fuel in our cars to the medicines sitting in our cabinets, every jagged line on a masked spectrum is a tiny, beautiful clue to the incredible logical architecture of our microscopic world. Thank you so much for joining me for this explainer. Keep your curiosity sharp, and I'll catch you next time.